Okay, good afternoon, everyone. In previous weeks, we have covered two types of proof methods to prove statements, theorems, axioms, and or conjectures, and then also for disproving statements using counterexamples. So these three topics we have covered in your proof lectures. Today we will study about last proof method, and it falls into the category of indirect proof methods. We have two. We will cover one of them today, and that is included in your midterm as well. Proof by contradiction. It is an indirect proof method. The last ones, that mathematical induction and direct proof method, they are direct, as the name suggests, direct proof methods. Okay, so in each of the proof techniques, we have a structure of how to write it. For example, in your direct proof method, what we have is, the structure is that so the structure in direct proof is that if a simple statement is given to you, what you do is you rewrite it in the form of a conditional statement, then if and then statement, and after that, whatever is after the if, that is your hypothesis, you assume it to be true in your direct proof method. And whatever is after then, that is the conclusion, you show the proof for that conclusion. So that is the structure of direct proof. And then in mathematical induction, again you have a very detailed structure. You have two steps, basis step and inductive step. And in basis step, you have to prove something. In your inductive step, you have to show two things. One is the assumption for any integer, any arbitrarily chosen integer. You show the assumption for that to be true. And then second thing that you show, the proof that you show is for the next term after k. So that is the structure of mathematical induction. In indirect proof, similarly, we have a structure. What you do is, I'll go through the steps according to the book. So first of all, you suppose the statement that you have to prove is false. You suppose the original statement that is given to you that you have to prove, you suppose it to be false, and then you take its negation and you suppose that negation to be true. Then you show a contradiction in the proof of the negation, and then you show the proof for it to be false. And based on that, you conclude that the original statement that is given to you, that is true. What does it mean is, in your first lecture, propositional logic, we covered this concept that if a statement is given to you, a statement can either be true or it can be false at one given time. So if this is your original statement, in proof by a contradiction is that you suppose this statement to be false, and then you suppose this negation of the statement to be true, then you show the proof for it to be false. Okay, this is you find a contradiction in the negation of the statement, and when you show the proof that this negation is false, automatically you reach the conclusion that the original statement is true. Okay, so you show the proof for this part, and based on when you show that it is false, you conclude that the original statement is true. This is the structure. Okay, let's look at it through an example. let's say a statement that there is no integer that is both even and odd. You have to prove it by the method of contradiction. So your first step will be that you suppose its negation to be true. What will be the negation for this? First, you have to identify what type of statement it is. It's a quantified statement. We have covered two types of quantified statements. One is your universal statement, and second is existential statement. So the keyword no tells us that this is a universal statement. There is no integer that is both even and odd. Identifying this will help you in writing the negation. So its negation will be that there exists at least one integer that is both even and odd. Then you take mathematical steps, you show contradiction in that, and you prove that negation to be false. Based on that, you say that the original statement is true. How? Again, you will be using the definitions or symbolic representations of even and odd integers. So your first step was, if I write it, there is at least one integer that is both even and odd. If you transform it into, now you have to prove this. So if you transform it into the symbolic representations of even and odd integers, what does it mean? That there is one integer, let's say x or any n, whatever, that is both even, this is the definition of even, and odd. So this is the definition of odd. And what we have to show is that, how do we show it? Like this. Like this, okay? Now, here on you have to show mathematical steps and prove it to be contradictory or false. How? That if we bring the 2b on one side, on the other side we are left with 1. And if we take it common, 2 common, and then if we simplify it further, so this was our last step. Now this is where we have reached. Now you see, we know that a is integer and b is integer. From the first topic, the conceptual, the concepts that you need to know when before writing the proof, we covered that difference of integers is integer. Sum of integers is integer. Product of integers is integer, right? But what do you see over here? Is 1 by 2 an integer? No, right? So, but on this side you have integers. So here you have a contradiction. This is integer because we know that difference of integers is integers, and we have already established that a and b are integers based on the definitions of even and odd integers. But on right hand side, what do you have? Not an integer. So this is not possible. It's a contradiction, right? So based on that, you say that therefore the supposition that both that there exists an integer, I will write it in short, is false, but you have to write the complete sentence. and this establishes that the original, therefore the original, or you can write hence over here, therefore original statement that there is no integer that is both even and odd is true. Okay, so this is how you show the proof for the contradiction. You negate it, you show the contradiction or the falsity of the negation, and based on that you say that the original statement is true. Okay, is it clear? Understand? Yes? No? Yes? Okay. One more example. So for these topics, you should know the definitions of rational numbers, irrational numbers, even, odd, prime, composite. That is a prerequisite for that. How do you represent those? For example, here we have the statement, sum of any rational number and any irrational number is irrational. So what, and you have to prove it by contradiction. What will be the first step? Anyone? What will be the first step when you have to write, when you're going to write the proof for this? Anyone? Yeah. Yes? This is a universal statement because you have the keyword any. So negation will be an existential statement. So what will be that? This negation will be, let's say, let's represent this statement with P. So its negation will be that the sum of any, you have to use the rule over here for negation of existential statement, where you know that the hypothesis, in the negation, hypothesis remains true, conclusion becomes false, right? So the sum of any, what will be its negation? There exists some number that such that it's some rational number, some irrational number, such that the sum is rational. You take the opposite of this one. Okay, so you negate it. What will be its negation? If it is, let's say, it's not irrational, even is given. So in its negation, it will become odd. If it's irrational, in its negation, it will become rational. If, let's say, over here it was in the original statement it was rational, in its negation it will become irrational. So that you have to you have to analyze and write. Okay. So its negation will be that the sum of a rational and an irrational number, this was the hypothesis, is in the original statement it is irrational, in its negation it will be rational. Now here is your negation. Take mathematical steps, plug in the symbolic representations of rational and irrational numbers, and then show contradiction in that. Show contradiction or falsity of this negation. And then based on this, Okay. You wrote down the negation. I will not write it again. Don't know what's the problem with this. But anyway, it's negation will be the sum of a rational and an irrational number is rational. What does it mean? That let's say, let's write that down in the form of symbols, the definition. Okay, so for rational, how do you represent it? How do you represent a rational number? Yeah, but like, how do you represent it? Yeah, yes. Where we know that q is not equal to 0, and then we have sum of rational numbers. So here is our rational number, sum, and any irrational number that we can take as s, x, whatever. And its sum is equal to, our negation is rational, right? Again, it means that we have to, let's say, because rational, so x over y, where y is not equal to 0. Now here manipulate it in a way, write mathematically, apply mathematical concepts over here, and then show contradiction in this. Okay, so you have to show it in the, from the perspective of irrational number, because you have to prove this statement to be true. So if we further analyze it, this is our irrational number. Let s equals irrational and the other ones are rational. Okay, so x over y, if we bring the p over q on the other side, what do we get? Yes, what will we have over here? Whatever it is, if it is, it will be like this, right? Isn't it? Negative, but see, like this, because it's a division, and after that, we will have. Oh, I'm doing something wrong. Sorry. But we will have a positive over here. Let's say, let's look at it in terms of negative. Okay. Let's say we get this, but we know that what we are concerned with is that we have to show that on this side we have a different type of number, and on this side we have a different type of number, and if we take the common, q, then we have xq minus p y. Now we know that x is integer, q is integer, p is integer, y is integer, y is again integer, and q is integer, right? All of these are integers. Then we know that product of integers is integer, difference of integers is integer, right? So all of this is integer, and yq is not equal to 0. Why? Because from this, okay? But here you see all of this is in the form of what? Rational number. But here what do we have? Irrational. So we have a contradiction over here. On the left hand side we have irrational number. On its right hand side we have a rational number. And this is from the this is the fundamental understanding or concept about irrational numbers, that they cannot be written as fraction of integers. Okay, so that you should know, that irrational numbers, they cannot be written as a fraction of integers, but rational numbers, they can be written. So again we have a contradiction, and based on this falsity of the negation, we can conclude that the original statement, or you can copy the whole statement over here, that the sum of any irrational number is irrational. Because what we have proved that the sum of a rational and irrational number is rational. We have proved this statement to be false. Okay. So if this was P and the negation was this one, we have proved this to be false. So this leads to the conclusion that this original statement is true. Clear? Understand? Yes? No? No. Okay, what part, what step, what part you don't understand? The whole, oh. It's okay. Let me explain to you first these steps, the structure of the proof by contradiction. First, you need to know the structure. What do you do? A statement is in proof when you have to prove a given statement using proof by contradiction. First, you negate the statement. Next, you show the negation to be false, or you show that there is a contradiction in the negation. And how do we, let's say, this was our original statement, okay, represented with P. And in the first step, we have to negate it, right? This is from your proposition. And if you look at, if you remember the truth table for a statement and its negation, we know that if the negation is false, it means that the other one is true, right? So in proof by contradiction, this is what you have to show. Okay, this part is what you have to show, whatever I have shown over here. All of this is this. Okay, when you show this part, the proof for this part that the negation is false or there is a contradiction in the negation, based on that, automatically the actual statement that is given to you in the question, that becomes true. Because a statement cannot be true and false at the same time. Okay, it can only be true or it can be false at a given time. Clear? Now, clear? Yes? Okay. And conceptually, that what type of integers or what type of numbers are given to you, how to represent them, that you need to memorize. Okay? For example, how do you show a general formula for even integers? You should know that. That is memorization part. 2k or any variable means when you multiply any integer with 2, you get an even integer. Then for odd, you should know the formula. 2k plus 1 means when you multiply 2 with any integer and then add 1 to it, you get an odd number. Okay, so this you need to memorize. Then for I will tell you about the types of integers that we have come across until now. Even and odd we have covered starting from your direct proof, and rational also we have covered those in direct proof. How do you represent those? Let's say we have a rational number, this. How do you represent it? You represent it as a fraction of integers, where means numerator and denominator, where b is not equal to 0. This is the formula for a rational number. Okay, so these symbolic representations you use in the proof to prove something. For irrational number, what you need to know is that you don't have, we don't use, in the scope of this lecture, we are not using the formula for irrational, but concept you should know that an irrational number cannot be written as a fraction of integers. Okay, if rational can be written, irrational cannot be written. Okay, this is for rational and irrational. Then what other types of numbers we have come across? Prime and composite. For that you need to know that what is the concept of prime numbers, what is the concept of composite numbers. So that we have covered in I think direct proof or counter example, one of these. Okay, clear? Is it clear now? Yeah, clear? Okay. All right. This is the same thing that I have explained to you. Here we used P, Q and XY for rational number, and here they are using a over b. Variables, whatever you use, just the representation should be correct, like this one. This is the rational number, this is irrational. When you add them up, this was the negation actually. This was the format of your negated statement. Mean that sum of rational and irrational is a rational number, where a is integer, b is integer, c is integer, d is integer, based on the definition of rational numbers. And based on the definition again, b is not equal to 0, and here d is not equal to 0. So if both of these are not 0, then it means when you reach over here, product will also not be 0, because none of them is 0. Okay? So this is your conceptual like base for reaching the conclusion. Clear? Okay. Then we have one more question, that the square root of any irrational number is irrational. What does it mean? First, you have to write the negation. Let's say this equals to r. Its negation will be square root. Let's say we take any number represented like with x. Let's say that x, its negation will be that this is how you represent the square root. Yeah. And then take the steps. In the second part, you have to take the steps and then find a contradiction and or prove negated r to be false, and based on this establish that r is true. Clear? These are the steps. This is the negation. Take steps, mathematical steps, find a contradiction or prove negated r to be false, and based on that establish that the original statement is true. So here you have, again here I will write these down over here. So your negation was that square root of x is equal to a rational number where b is not equal to 0. Now if you simplify it, because you have to show it in terms of x, right? So if you simplify it, remember this is irrational. Again here, this is irrational. And again here you have a rational number, because we know that product of integers is integer. So here you have a product of a into a, and then here b into b. So this is again rational, and here you have contradiction. And therefore the original statement was represented with r, so therefore r is true, and this negated r is false, because you have a contradiction over here. True? Correct? Understand? Clear? Okay. So this is you are indirectly proving the statement to be true. Okay, you are first taking its negation, then proving that negation, finding a contradiction in the negation, proving that to be false, and then based on that you are saying that the actual statement is true. So indirect method. Okay, is it clear? Understand? With this, you can also look at examples in your chapter 5 It's chapter 5 or 6, one of these. Yeah, 4, sorry. Okay, you can find more examples in the exercises of chapter 4 in the book, in your main reference book, and try solving. If you don't understand anything, you can ask me. With this, we conclude our proof topic. Any questions from any proof technique? Direct mathematical induction, or counter example, disproving using counter example, or and this proof by contradiction. Any questions? No questions? Rational? This, actually, you can say that this, and here A is integer, B is integer, and this, sorry, B is not equal to 0. Denominator cannot be 0. You can use any variables over here, but this is how you show the rational number. Okay. It could be, usually it is shown as P over Q, where Q is, this we covered in one of your previous lectures, when we were covering divisibility and floor ceiling. At that time, I taught you this one. Clear? Now? Okay. Any other questions? No more questions? Okay, then we will start next lecture. Which is set theory. Can anybody tell me what a set is, generally speaking? What is a set? Anyone? Anyone has studied this topic before? Sets? Yeah. A set is a collection, or a set is a collection of definite and separate, or not necessarily unique, but separate elements. Okay. How do you represent a set? There are two ways. Okay. One is, if you have a set with a small number of elements or finite number of, not necessarily finite, because even in a finite set you could have a big number of elements. So when we have a small number of elements in a given set represented with variable A, you enclose all the elements in a curly bracket and then write down your element 1, 2, 3, 4, and up to n. So this is one way of representing a set, or writing the set notation. Another more formal way of writing a set is, you write it in the form of a variable, let's say x. It belongs to, again, the concepts from your previous lectures, it's coming up over here, that x is an element of any given set. Here you can say a domain, this could be any set, such that, or where you have the property, or it could be a function, a property, or okay. This could be any property. Okay, so you see, it's similar concepts are being applied over here when we studied predicate logic. Okay, so this could be any mathematical expression or any inequality, any equality, and this is how you write the set notation. Especially when the set is like a set of real numbers, where you cannot represent each individual element present in the set of real numbers here in the form of separate elements. Okay, so there this is feasible. This method is feasible to use. Okay. This I hope you already know. What does it mean? It means belongs to this variable. This element belongs to a given set such that P of X. Okay. Then after that we prove we have a relationship between two or more sets, subsets, superset, proper subset. So first one is that a given set A is a subset of a set represented with B. Okay. What does it mean? That if we write it in the quantified statement form, how do we represent it? That for all X means all elements, if X is an element of A, then X is also an element of B. So that is that relationship is shown over here. Okay. If X is an element of A, then X is also an element of B. So only when this statement is true can we establish this relationship between two given sets. Okay. And what does this mean? That A is not a subset of B. How do we show it? That there is what does this mean? That there is at least one element in set A that is not present in set B. In that case, A cannot be a subset of B, because according to the relationship, subset relationship, if we have to determine whether A is a subset of B or not, you need to check the elements that are present in set A. All of the elements, they must be present in set B for A to be a subset of B. Okay. Then we have a proper subset. Proper subset is that, to explain it in simple terms, that let's say if this is true, what does it mean? That all of the elements are present in B, but B has at least one element more, okay, as compared to A. And from here we can tell that a set can be a subset of itself, but it cannot be a proper subset of itself. Okay, so these concepts, relationships of subsets, you should know. A subset can be a subset of itself, but it cannot be a proper subset of itself. Why? Because for there to be a proper subset relationship, one element in the superset must be more than as compared to the subset. Okay, do you understand? For example, let's say A is equal to 1, 2, 3. B is equal to 1, 2, 3, and 4. Now, is it true if these are the sets? Yeah. And no? How come? And then, is this also true? Yes. Why? Because B has one element that is not present in the set. Okay, so A is a proper subset. Let's say this was A and this was B. Now, is it true? This one? Yeah. This one? False. Yeah, so not true. Okay, understand? For proper subset, you mean? For proper subset, for this to be true, there should be at least one more element in B that is not present in A. Yeah, one more, at least one more element. Okay, so it means the set B should be greater, like bigger, okay, as compared to set A. And in this relationship, this one is known as superset, and this one is known as, the smaller one is known as subset. Clear? Okay. So let's look at it through an example. Okay, let's say you have set A which has one element, and set B where you have one, and then another set containing element 1. So is A a subset of B based on this information? Yes. Is A a proper subset of B? Yes, because there is one element in B that is not present in A. Clear? Okay. And also, just like on this side note, that when you have one element in a set, you call that set as a singleton. Okay, so there are names for sets based on the number of elements they have. Okay, so set with one element is also called as a singleton set. Now we'll apply the proof concept over here to determine the relationship of subsets. How do you show the proof for whether one set is a subset of the other one or not? There, what you need to remember, this definition. This one. This. You use all of this to write down the proof to determine the subset relationship between two sets. I'll go through it first and then show you a practical example. Okay. Okay, let me go through this information first, because we define what it means for one set to be a subset of another by means of universal conditional statement, the statement that I mentioned to you, this one. So this is the universal conditional statement for this relationship. Okay, we can use the method of direct proof to establish a subset relationship. Okay, such a proof, what it is called, an element argument, and it's the fundamental proof technique of set theory. So we use the direct proof method to show the proof for subset relationship between two sets. Okay, and here is the concept that we need to know, that when a set is a subset of the other. Let's look at it step by step. We are using direct proof method. So let's say you have two sets, one is set X, one is set Y, and to prove that X is a subset of Y, first you will suppose, again, the same method, you will suppose the hypothesis to be true and you will show the proof for the conclusion. Okay, so here our hypothesis is that X is an element of A. Okay, so we will suppose that to be true, that X is a particular but arbitrarily chosen element of X, means X is an element of set X. This we will assume to be we will assume it to be true. This is our hypothesis, and then we will show that X is also an element of Y. This is what we have to show the proof of. Okay, to show that X is an element of Y. X is a subset of Y. Now let's go through the steps. This is the explanation. Let's go through an example for that. Now just like we have symbolic representations of even, odd, those type of integers, similarly, we can represent elements in a given set based on some formula. Means whenever we will take the closed formula or general formula, whenever we plug in any integer, we will get the element of that particular set. So that is what is given over here. In set A, you have elements m, okay, and how you can get that element? This is the formula for that, and where this R is, it belongs to set of integers. Okay, so whenever you plug in any integer in the position of R, and then you use this formula, you will get the element for set A. This is what it means. Then for set B, how the elements for set B can be found? The element is equal to 3 multiplied with S, where S also, it also belongs to set of integers. What does it mean? That when you plug in any integer in the S and then multiply it in the place of S, then you multiply it with 3, you will get the element for set B. Okay. Now what you have to show is, in first part, you have to outline a proof that A is a subset of B. In part B, you have to prove that A is a subset of B, and then you have to, in the third part, you have to disprove that B is a subset of A. Okay. So first part, how do you show it? First, you identify starting point. What will be the starting point? You will assume that M is an element of A. Because this is in the hypothesis from the question. Okay. M is an element of A. This will be your assumption. This will be the starting point because this is the hypothesis. And what you will show, the proof of that M is also an element of B. This is what you have to show the proof of. Okay. Now M and N, they are the common variable for all the elements. You can take any particular M, represent it with another element, like another variable like X. X is any particular element in the set A or set B, and it could be any variable. Okay, it could be X, Y, whatever you take. Okay. So, and then you will show that X is an element of A and X is also an element of B. This will determine that A is a subset of B. How? Over here, if you see. So you will keep these definitions of or symbolic representations of the elements in set A, symbolic representations of the elements in set B, and then you will start from here. You have to show that A is a subset of B. Okay. So we know we are taking any M and representing it with a variable X. It equals to, what does it equal to? 6R plus 12. And then what you have to show, that 6R plus 12 means the element in set A is equal to element in set B, 3 into some integer. This is the for your definition of elements in set B. And then from here you will take mathematical steps and you will reach a conclusion that this equals to 3s. Okay, because this is the definition of set B, and then based on that you will establish that A is a subset of B. How? If you manipulate it, we can take common, because we need to show it in this format. So see, if on the left hand side you can make it equal to the right hand side. So if you take 3 common, because you need to have 3, what you will get over here? What you are left with is 2r plus 4, okay? And then you have 3 and some integer or s, whatever. Okay. You can write in any way, doesn't matter. Some integer, or you can write s, it's okay. And we know that r is an integer. We know that 2 is an integer. So product of integers is integer. Then we know 4 is an integer, and then sum of integers is integer, right? So let you can take any, or you can take s equals 2r, whatever is in the bracket. So same steps as your direct proof. Then you can simplify it. 3 into s is equal to 3 times some integer. So here you have reached the conclusion that left hand side is equal to right hand side, means you have shown that the element in set A is equal to element, or it is also present in set B. And how in the question it was defined, the elements in set B, 3s. So you have shown that the element in set A is also present in set B. So based on this, you can determine, or you can conclude that A is a subset of B. Does it make sense? Is it understandable? Yes? Okay. We can, if you don't understand, I can show you one more example. For disproving, you will need to show a counter example. Okay. Okay, is this clear? Yes, no? Okay. For disproof also, you will need to you will need to show a counter example for that, and there you will take your integer as a base, and then show that the conclusion that you reach, it's not an integer, and that will give you the counter example. That is what has been done over here. This is your element in set A, and then when you manipulate it, if you take common on both sides, if you take 3 as common on both sides, you can reduce it to 2r plus 4 is equal to 1, and then this is what the integer was, right? So you will write the equation for this integer and see if you get integer on your right hand side or not. So you get 1 minus 4 is minus 3, and then divided by 2, okay, because here it is multiplied, so divided by 2. Is this, we know that r is an integer from the question, from here, this r belongs to set of integers. But is it true, this one? This is integer, we know, but is this an integer? No. This is not an integer, okay? So here you have, again you have a counter, this you can take as a counter example, okay? And based on this, you show the proof that B is not a subset of A. So same concepts you are applying the concept of, or the steps for direct proof method in showing that A is a subset of B. Then you have to disprove that B is a subset of A. For that, we know, for disproving, we find a counter example. Only one counter example we need to find, and we can plug in the values for that, and here it is in the context of left and right hand side not being equal. Okay, so this could be if let's say it was rational and irrational numbers. Here, if you had to show that you have irrational number on the left hand side and on your right hand side, it should be an irrational, but because you have to show the counter example, so they would be different. On both sides you will have different types of numbers. That will be a contradiction and that will be false, so that will be your counter example, okay, to prove something to be false. Okay, clear? Yes? No? Okay. Right, next we have set equality. Two sets are, one thing is that a set can be a subset of itself, right? One is that a set is equal to another set. What does it mean? That it should fulfill two conditions. It should fulfill first condition, that for the two sets to be equal, that A is a subset of B, and this is your first condition. For A is equal to B to be true, it should fulfill that A is a subset of B and B is a subset of A. Only then we can say that A is equal to B. So that is the concept of equality, and we will not go into the proof of that, but I will tell you how to show the proof, the structure. What does it mean is that when you have to show the proof, again you will be using direct proof method, and in your previous example we were only showing the proof for this, but when you have to show the proof for equality, you will first show the proof for this, for the first condition, and then you will show the proof for second condition, and then you will reach the conclusion that A is equal to B. We will not go into the detail of that. Okay, that is not included in your test also. So next is the concept of Venn diagrams. Who knows about Venn diagrams? Venn diagrams? Yes. So what are they? What are they used for? Yes, and? Yes. Yeah, correct. We use Venn diagrams to show relationships between sets and to show the set operations. Okay. In set operations, the same thing that you said, that how many elements are shared, and based on that we show different types of operations. So we can show the relationship between two sets. For example, if we want to show this relationship in the form of a Venn diagram, okay, here A is a subset of B. How you can show? You will have we know that B is a superset, so bigger set, and then this is a smaller one. So this tells us that A is a subset of B. Okay, and we can also say that A is a proper subset of B because there are some elements in this region of B that are not present in A. Okay, and when two sets are equal, we know the condition for that A is a subset of B, B is a subset of A. Therefore we have it's A is equal to B. So it means that the region or the area they cover of the elements is same. So single circle. So this is how we can show the relationships between two sets. And if we want to show that A is not a subset of B, how do we show that? We should know the concept. What does it mean that this It means that either no elements in A and B are shared, or we can say, so that is represented with two separate circles, okay, A and B, or we can also represent it with overlapping, this one. Now, why we are using this diagram for showing that A is not a subset of B? Anybody? This is straightforward because no elements are shared. So A is not a subset of B. We have different elements. But why? How do we show it like this? What does it mean? Yes. So, but we do have some elements in A that are also present in B. But still, this is used to show that A is not a subset of B. Why? Yes. You're almost there. Yes. Yes. So, for A to be a subset, they should all of these elements, these elements should also be present in B. Okay. So that is why we can show it like this, because this tells us that there are some elements in A that are not present in B. Okay. So that is why A cannot be a subset of B. Okay. Although there are some elements that are shared in the overlapping region, but there are some other elements that are in A that are not present in B. So based on that, A cannot be a subset of B, because for A to be a subset of B, all of the elements that are present in A must also be present in B. Okay, clear? And this is pretty straightforward. Here, A is not a subset. A is rather a superset. Okay, so this is not true, but this one is true here. Okay, this is true. Clear? Then this one is again as a base for your concepts in set theory. What type of sets we have, the relationship between some common types of sets, these you should know, and some notations that for the common sets. For example, Z. If this is there, what does it mean? This is set of what? Integers. Okay. So Q. This is the notation for set of Q. Rational numbers. Yeah. And R is for set of real numbers. And then we have one more, P, that is for irrational numbers. Okay. So, but what is the relationship? These are common sets that you will come across in your set theory topic. So you need to know the relationship between these three sets. We will not look at irrational, we will look at rational, integers, and real numbers. What is the relationship? Now here you have to memorize it, that set of integers, this is a subset of set of rational numbers. Okay, all the elements that are present in the set of integers are also present in set of rational numbers. Okay, this is established, so you need to know that. Then set of rational numbers is a subset of set of real numbers. Okay, so this is the relationship between these three sets, and we can also say that set of integers is a proper subset of set of rational numbers, which is a proper subset of set of real numbers. Why? Anyone? Why? Yeah. Real numbers have types of numbers that are not present in Q, but all elements present in Q means rational numbers are present in R. Okay. Same goes for the integers and rational numbers. all the elements of set of integers are present in Q, but there are some elements in set of rational numbers that are not present in set of integers. So we have this type of relationship of proper subsets and subsets. This relationship you should know, and mostly we also have another type of set, universal set. This is considered to be the biggest set available, and when we show our Venn diagram in this format, means rectangle, and then we have circles inside the rectangle. This rectangle represents the universal set. And when the universal set is not given to you as a set of some finite numbers, or it is not defined, mostly it is defined to be a set of real numbers. Okay, this is in the scope of this lecture. Now operations. 4 types of operations we will cover. One is union, then intersection, and then difference, and then complement. This is for union, this is for intersection, then difference of, it could be difference of A and B, or difference of B and A, and then complement of a given set. Now here we will use universal set also, because this will be in relation to the complement. When we have to find out complement of a given set, we will refer to the universal set. Okay, how do we define it in the set notation form? A union B. How do we read it? That X is an element of a universal set such that X is an element of A, or it is an element of B. What does it mean? That in a union of 2 sets, we need to have at least 2 sets for there to be union relationship. That one element, if it belongs to either one set or the other set or both of the sets, then we can take, that is the union. Okay. For intersection, in the intersection set, what we will have, what type of elements we will have? Only those elements that are present in both of the sets. Okay, so we will have, we will perform AND operation over there. Okay, so only those elements that are present in both of the sets. Then for difference, what we will do is, let's say you have to find the difference of B and A. We will look at the set B, the elements of set B, and then we will exclude all the elements that of set A that are present in set B, and whatever we are left with of set B, those will give you B minus A, or difference of B and A. How? Let me show you. For example, you have to find out B minus A over here. So B is D, E, F, G, and A is A, C, E, G. So what you are doing over here is, you are looking at set B and excluding all the elements that are present, that are common in set A, remove them. So D is present in A. Is it present? Is D there in set A? What about E? So remove it. F, G, remove it. So you are left with D and F. Okay, so that you will write in the difference of B and A. Now let's say you have to find out A minus B, difference of A and B. Here you will focus on set A, okay, and exclude the common elements with set B. So A is not present in set B, so you will write that over here. C is not present, you will write that over here. E, G are present, so this will be the difference. Okay. So whatever set you have first, you will focus on that. Exclude the common elements, and whatever you are left with in this set, those will be in the answer. Those will be written in the answer. Okay. Clear? Now you can show these in the form of Venn diagrams, these operations. So in your A union B, what do we get? All the elements that are present either in A or in B or in both. So all the shaded area, that gives you the union. Okay. In your intersection, we said we will perform AND operations, means only the elements that are shared between the two sets. So the shaded area, that gives you those elements are present in the intersection of the sets. And then for difference, you exclude the elements that are present in the other set, and in the answer of B minus A will be this one. What about what we will have if, let's say, you have to write this down as a Venn diagram. So let's say this is A, this is B. So what elements will be covered? Which area will be shaded? Which area do I need to shade to represent this? With this or without? Yeah. Okay. So like this. And last one is complement. So for complement, it's easy. Whatever you will refer to the universal set. So you will see that whatever elements are absent, are not present in set A, they will be there in its complement. Okay. And there are 3 or more ways of representing a complement. This one, and this one, same thing. Okay. So whatever is not present in set A, but present in universal set, that will give you the complement of set A. Okay. It means that universal set excluding the elements in set A. Okay. And how do you show it? Like this. You will exclude all the elements that are present in the set and shade all the elements that are present in the universal set in any other set that is present. For example, if you had to find, I will show you another example. Let's say you have to find B complement. So which area will be covered for B complement? Yeah. Yes. Okay. Clear? No? Not clear? Okay, this we will cover in your next lecture. We will stop here for today. The interval notation and then finding unions and intersections of more than 2 sets, that we will cover in next lecture. Any questions from your group assignment? You have time, you can ask me. Group assignment or test. Also, first let me go through the instructions for your test that were posted yesterday. An announcement was also posted. Did you receive the email for rescheduling the rescheduled date of the test? It is rescheduled from week 9 to week 10. You have to mark your attendance. So week 9 to week 10 because of the Salesforce training. Okay, so you will have your test on 29th of November during lecture time. It will be of 1 hour and 30 minutes, MCQs. You will attempt it my times. And here, if you go to your test section on my times, you can find all the details, the topics as well. So let me go through this information about the rules and regulations. Please listen carefully. Okay, so your test date is 29th of November from 2 to 4 p.m. in the same venue. And you must bring your student ID along, okay? Also, attendance will be marked manually, so we will not mark your attendance via CAMS. So all the students must be present in the venue for, to attempt the test. Okay? And we will give you either attendance slips, separate ones, or we will give you attendance sheet to mark your attendance. And you, like students who have not marked the attendance on that sheet or list, they will be considered absent and a 0 mark will be given. And there will be no negotiation. I'm telling you beforehand. Scientific calculators are allowed, programmable calculators are not allowed. And for any rough work, we will give you papers, okay? So you don't need to bring anything, any paper or anything. You must be present in the venue 15 minutes before the start, okay? So 2 p.m. the starting time, please be here at 1:45 p.m., okay? And in case we have latecomers, no extra time will be given. Only one device, you need to bring only one device to your seat to attempt the test. Make sure that it is fully charged. Make sure that if there is any technical issue, you solve it beforehand. Okay? Clear? Understand? Okay. Yes. Yeah, scientific calculators are allowed. Programmable are not allowed. And test topics are also given over here. Propositional logic, whatever we have covered during the lectures. Okay? So for topics, within the topics also, if we have not covered any subtopic, it means it is not included. For example, in your propositional logic, we haven't covered rules of inference, so that is not included. All the other topics that we have covered, they are included. Refer to your lectures. These lectures are recorded. You can find them on My Times, okay? So whatever topics we have covered in propositional logic, in predicate logic, in your direct proof, disproving by counterexample, proof by contradiction, mathematical induction, and set theory. Whatever we have covered, that is included, all right? And your study resources are your first reference book, Discrete Mathematics with Applications by Susanna, and 5th edition, and your tutorial exercises and your lecture slides. In your lecture slides also, there is at least one example, but there are more than one example for each concept that we cover, okay? So the type of questions that you cover in your tutorial classes, they are also taught to you during your lecture class, okay? So lecture slides, tutorial exercises, and your Discrete Mathematics with Applications book. That will be your study resources, okay? Clear? Understand? Any questions? Yes, any questions? If no questions, then you can mark your attendance. Please mark your attendance. updated in the system after like 45 minutes or an hour. So you can just write down your name over here and I'll update it. I'll update it for you.
I can message you on Teams.
Oh yeah, yeah.
Thank you.
What is tell me what is your name?
I'm Adam.
Just send me and I'll mark it as update.
Madam, can I ask for the assignment? The data that I found, is it necessary to be in real life one? Those appointment data and those.
Did you find it already?
Yeah, I find it, but the data is like, I think it's not the in real life like those. Huh?
It's WS.
Yeah.
Where
In the K group.
there was one more case. There is no reference. There is no like how it was collected.
It's just a bunch of data like your appointment ID, appointment name, the patient ID, patient name, and the clinic name.
Usually when any data is uploaded on Federal or any
It's
other
real life.
data, no, not necessary.
Not necessary.
It can be synthetic, but then they explain based on what criteria they created this data.
But
You can find that information. Then you can write it in the content that this is how the data was collected by the like secondary source.
so I need to write the reference or what?
Yeah, reference.
Okay. Thank you.
Everything. You guys are seeing all these skills. I can't confirm that.
I finished one by one first, but my laptop just down and didn't save. Then just mark it, I just code for it.
Oh, you're not in group. Then you got
Yeah, that's easy. Wow. Shit, genius. No way,
It's an assignment, it's a test. If you have any problem,
No, you give feedback on YouTube,
you share yourself. Not the lecture.
okay lah, I just try to show
She responds to you. I can
Oh, yeah, you get the point, yeah.
like she did for
Yeah, I find it that any data can be used.
I can tell you this is right. That is right. You are going to the right direction. It doesn't matter. It's more.
Already done.
I just confirm my outline or my draft is correct, then I can just
Bro, every Friday you have dawah. It's not compulsory, bro. No, it's not. Everyone is very good. It's always true.
So I can like ask for or need to wait for the that's normal, I will do that lah. don't count.
Yeah, otherwise, for your personal use, you can search for the refund details. Each task is actually a problem, right? So you are using the, for example, we have just set theory concept to solve some real life problem, right? So if it can do that, that should be okay. You don't need to make it more complex. So it's not like, it shouldn't be like one instrument, like one system. It's not like that. So good enough to explain everything more, like just like when we have calculation. You take a sample out of it, so you can also find out what is it and you can use for it, right? So similar to this.
Data set there we have 23. So I just from the new Excel
New Excel.
about the field that I use. Oh, it's no need to do that.
I don't quite understand.
你跟他讲是，我现在highlight 了嘛，然后我tutorial是讲我可以直接可能我做个 Excel 重新整理出来，这样我要用的数据，因为这边有 ID 号嘛。
Okay. So like, we just take the data from here to convert another Excel, but the same also as same data. Just a new database that contain only the data that used.
Oh, if I understand it correctly, you mean that you have a data set, and in the report, in one question you want to show part of it, you want to use part of it, and in the other maybe other part of it also.
The original I also cite it yeah, I extract the data on maybe on the where submit because it's easy to see that.
Oh, you mean in the report, like what you show in the report? Yes. Let's say if I am understanding it correctly, that let's say you have a data that is that you are using. It has 500 records or 200 records. All of that you will not show in the report. You will take a screenshot of part of it, and then you will show.
The original I saw cite on the
You will describe the original data that you are using in the content. That, for example, it has these many rows, it has these many columns. The columns are this to this, but the capture you will take for some.
yeah, I read from this form is also explained.
Yeah, I should tell this. This 100% I should.
Oh yeah, this one.
I just scared you want me to explain the code.
This is you
don't
don't
use
need to
ether.
like,
I just
convert
like
all of this
convert to sum or something like that.
representative units.
So if I do like that, like the Excel, like the photo also no need already.
Capture for this you can show me. Like this one is okay. You can just take a capture of this and then paste it there. You don't need to, you don't need to write all of these in the table format. You can only just take a capture and then explain about it, describe it. It's called data set description. There you describe everything.
Just
How
like
many.
reference, right?
It's like when you go to Kaggle or any other databases, all of the data set is present there, and then they introduce the data set. They explain how many. I mean, they tell how many rows are there,
the description.
how many columns are there, what this data set is about. So all of that is included in how it was collected. So, and then when we, for example, as researchers, we use in our report or in our research, we don't show all of this in table format. We take a capture of that and to give an idea to the reader that this is the output, this is the structure of the data. And then we write the description of it and provide reference. So just whoever is not interested in those yeah, you see, you are explaining over here that C1 is, it means this, how you are defining the values. So it's enough. More than this, you don't need to, if it is not relevant to, if this is enough to show the content of or the answer, yeah, then it's okay. This should be enough. Just like in your, you have application of graph also in your task, right? Yeah, there also you don't need to, for example, scope you are defining. For example, if you are taking data set from for different cities, you don't need, for example, Malaysia, the cities in Malaysia, you don't need to take all the cities of Malaysia and then show the graph for that. Just take a representative, take 9, 10, which will give you a good graph.
So far it's not enough.
This is okay because this is sets. This is Venn diagram, right? For graph, it's different. So there you have in your graph what you there you have like the nodes. They are the locations, and then the distance between those they are shown as x's. That makes a graph. So you have two things in a graph. You have nodes and vertices, and you have edge. So there you can show like 9 to 10 nodes. You don't need to go up to 20 or 30 or 15. Just like here also. Here you don't need to write it.
So we just pick like for example like 9 and we draw like the connection and just take picture like
It could be 9 cities. It could be 9 any it would be edge. So it could be like same location, like different locations in the same city. So 9, 10 up to those. Like just enough.
yeah, but like the lines represent the distance, right? So like can I like maybe like go to Google and ask like what is the distance, for example, from like Selangor to Penang, and I just find the distance and I just write that
You can even take a screenshot from there. As many figures you have, it is like it is better than the word. So just explain the figure. Include a figure if it makes it easy. Just think from the reader point of view. What will make us attractive towards the report? Adding figures and all that, because it will explain to me, or it will be easy for me to read. So you can include as many figures as you want. You can just take from somewhere and then just provide a reference if it matches the answer in your task. If you look at the marking group,